a long-chain carboxylic acid. It's derived from fats. Fats are long-chain carboxylic acid esters, and they're related to butter and margarine and so on in our fatty tissues and so on. So when you treat such an ester with methanol, this is an ethyl ester treated with methanol as a solvent, so you have large excess of that. You can use acid or base, both works. The base, of course, has to be the alkoxy of the corresponding methanol, or sometimes you just use a small amount of sodium hydroxide, which is then drowned out by the huge amount of methanol around, and you generate methoxide in this way. That makes the new ester high yields and no problem. So here we have an example where we use a cyclic ester, so this is a lactone, and we want to trans-esterify by using this alcohol here. So when we have a cyclic ester, remember this is one case where, because it's cyclic, the leaving group as it leaves stays attached to the molecule, okay? So it doesn't leave into outer space. It just detaches from the function, okay? But it's still connected by this carbon chain. And so with acid, indeed, you protonate and you get additional elimination of this hydroxy here, and it eliminates this hydroxy function, and you get this product, which is, if you look at this, is a nice functionalized building block for other syntheses that you might think of. So here's a teaser question. This specific example here only works with acid. And this drives home a point that you should also keep in mind, namely, if you have a choice of two reaction conditions, acid or base, it's worthwhile thinking about this for 5 seconds to see whether there might be an advantage to using one over the other. And this is the case when you have other functions in the molecule that may be perturbed by one set of conditions but not the others. For example, if you have an alcohol that has a ketal, acetal down the line, acetals are sensitive to acid hydrolysis. So they're using a base to hydrolyze an ester or do a trans-esterification may be advantageous. Okay? Conversely, there may be some functions that may be sensitive to base, and so you want to prefer doing acid. And such is the case here. In principle, trans-esterification can be done with acid or base, but this one only works with acid. So the prime question this late in the day is why? What's wrong with hydroxide? Anybody venture a guess? Yeah. That's a good point. The final product may not be stable to sodium hydroxide because you'll deprotonate and it will do additional elimination here and actually revert back to the corresponding lactone. Okay? So basically you're saying, in principle, this would go backwards. Well, it is an equilibrium. And the equilibrium lies on this side because entropy-wise, you're better off opening the ring and there's a slight amount of ring strain in this structure. But that's the kind of thinking I want you to do. What about the starting setup? Is there something wrong with particularly this material in the presence of base? Does that look familiar? Chapter 9? These are the ideal conditions for an intramolecular Williamson ether synthesis. Okay? So that guy with base will be in equilibrium with O- here. So hydroxide will every now and then pull off the proton, make O-, and the O-, of course, that's what you need in order to do the additional elimination. But he's got a faster way of reacting, namely intramolecular SN2 on this bromide, kicking out the bromide. And that gives you the 4-membered ring, 1, 2, 3, 4, 4-membered ring ether. Okay? Now you might say, oh, wait a minute, the 4-membered ring ether, it's strained, it shouldn't form. Not true. The reason that we, in all the chemistry we discussed this semester, we stayed away from strained rings was not because they're not formed, but because they're formed reversibly. And so you go to a 3-membered or 4-membered ring, but it just comes back and eventually finds its way to a more stable product, but normally a 5- or 6-membered ring. In the Williamson ether synthesis and related reactions that you may have encountered, this is irreversible. Okay, you get displacement and then you're stuck. The ether doesn't reopen with bromide, right? And so it's a kinetic product, and the molecule is basically fooled into making something it doesn't really want to make thermodynamically, but it's as far as strain is concerned, but it's pushed into that, and then it doesn't come back. Okay? So that's the problem with base in this reaction. Okay. Now let's move from oxygen-based nucleophiles to nitrogen, and indeed amines will do this, additional elimination, and you get the corresponding amides. An example is here. Here's an unsaturated fatty acid, which is very much in the news, right? What is good for you, what is bad, cis and trans unsaturated acids. So this is one of those guys. And here the methyl ester with amine turns into the corresponding amide. Not bad yield, but notice the conditions. Terrible, okay? And the reason you need such high temperatures is because esters are with a neutral and uncatalyzed basic but neutral nucleophiles, not that reactive. Okay, so this is not a good way, although a possible way, to make amides. A much better way, actually, to making amides is go through the acyl halides and amines. Acyl halides are hot. Acyl halides do everything. When in doubt, use acyl halides. That's the bottom line. Okay, so this is a good plate. No, let's see. No, let's do this one before we have a break. So we have amines, and now we're turning to carbon-based nucleophiles, and as we've done for the other functions, in particular for the acyl halides, where we notice that if we take an acyl halide with a cuprate, you get additional elimination, and you get a ketone, and the ketone is stable to the cuprate reagent, so we can turn an acyl halide by additional elimination to the corresponding ketone. In the case of an ester, is this also feasible? Well, first of all, you can react an ester with a Grignard, and you find that you get a totally different product. Out comes this. So what has happened here? This is really quite bizarre. And you notice we're using two equivalents of a Grignard, and if you stare at the product long enough, and there's a color coding, there are actually two of these groups, two propyl groups that wind up in the product, and what we get is a tertiary alcohol. In fact, what we get is a tertiary alcohol that is symmetrical, because two groups are the same. So retrosynthetically, this is a powerful disconnection. If you remember this process, and if you remember to stare at a tertiary alcohol and look at it with respect to symmetry, if it's symmetrical, you can actually cleave these two bonds and make them part of a Grignard and turn this piece here, this 3-carbon piece here, into an ester. Any ester, because this guy leaves as a leaving group. So this could be methoxy, alkoxy, any ester, doesn't matter. That moves away as an alcohol and is thrown away. So it's this piece that gets converted into this tertiary alcohol. And this happens for all esters. One exception is the smallest ester possible, methyl formate, which has this 4-methyl group. Looks like an aldehyde, but it isn't. It's an ester. This 4-methyl function here. When you do that, double addition, of course, you have a hydrogen left here, so that's a secondary alcohol. And that can only be derived from a formic acid ester. That is symmetrical. So for both of these, we have symmetrical alcohols, either tertiary or secondary, in which we have two of the alkyl groups are the same, and that's why they're symmetrical. So how does this go? And it goes as you might have expected, very similar to what happens with acyl chlorides and organometallic the cuprate, except that it doesn't stop at the ketone stage. So the Grignard does what it's supposed to do, add to the carbonyl in the usual way it adds to the carbonyl of aldehydes and ketones. And so you get the addition product, and you sit there. And this doesn't stop here, however, because you have an O- here next to the magnesium plus. I've written the resonance form where there's actually a bond, because there's a certain amount of covalency to that bond. But you can write this as a salt, and we have done that, O- magnesium plus. And the electron pair comes in here and kicks out the leaving group. Okay? And that generates an alcohol. And that alcohol is reactive, as we know. A ketone. And that ketone is reactive, as we know, in the presence of a Grignard, so it just reacts once over. So in the case of acyl halides, we solved it with the cuprates, okay, where the cuprates didn't attack this. But with the Grignard, for an ester like this, you go all the way. So you add a second R group. And on hydrolysis, aqueous workup, this is what gives you the tertiary alcohol. So that's a good piece of vocabulary to keep in mind, because, again, retrosynthetically, it means that you can cleave in a symmetrical tertiary alcohol here and here and relate all of this back to an ester that contains this R group and this carbon, and the red guys come from Grignard reagent. Now, can we do hydride reductions? We've done that in the case of acyl halides, and the acyl halides, lithium aluminum hydride will take it all the way to the alcohol, just like in the case of carboxylic acid, primary alcohol. But for acyl halides, we noticed that using a modified hydride, a modified lithium aluminum hydride, where we replaced 3 H's with tertiary butoxide, that guy had 1 hydrogen left, much attenuated, reduced reactivity, and that adds by hydride addition, and then just stops at the aldehyde stage. Okay? So can we pull off stuff like that with esters? And so I'm giving you an amino acid ester just for added variety here, but the ester, it's the ester function that is important. With lithium aluminum hydride, as I said, the atomic bomb of hydride reagents, that never stops. Lithium aluminum hydride takes everything down to the lowest oxidation state. Okay? So this guy turns this down to the primary alcohol, just as it would with acyl halides or carboxylic acids. Okay? So there's no stopping here. But can we treat this with milder reducing agents such that we can actually stop at the aldehyde stage? This requires that we add only once an H and then we stop. And indeed, there is a reagent. For esters, the equivalent to the modified lithium aluminum hydride in the case of acyl halides, it's this beast here. It's called diisobutyl aluminum hydride, is the common name, or short dibol. Okay? So notice it's basically a branch butyl group, 2 of them, aluminum H. So this is actually, to call this a hydride is a misnomer, because it's not a hydride. A hydride is something that's negatively charged. It's just a trivalent aluminum derivative. So it's actually an alane, okay? Similar to a borane. And notice that aluminum is right below boron, okay? So it forms very similar compounds. We've used boranes in hydroboration. You can make corresponding aluminum derivatives, and that would be called alanes. And they react with CO double bonds by a similar mechanism to hydroboration to CC double bonds. It's really a concerted type addition of, in the case of dibol, aluminum and H adding to the CO bond. But the end result is the same as if it had acted as a hydride reagent, because the H winds up on the carbonyl of the carbonyl carbon, and the aluminum, like all metals, winds up on the oxygen. And it does this only once, because then the double bond is gone, and since it's not really a hydride, although we call it a hydride, it just stops there. And if you do this at low temperatures, you're totally safe, and then you hydrolyze it, and out comes the aldehyde. So the bottom line is that lithium aluminum hydride does double H minus additions, or H minus equivalent, whereas these modified hydrides, or in this case alane, add H only once. And so this is so summarized here for an ester. In both cases, you get addition of H in the first step, the H minus equivalent to this carbonyl carbon, and the metal winds up here, okay? And I've written it because these mechanisms are not nailed down, actually. So, there's a lot of hand-waving here. But it's something like this. And nobody knows exactly what's actually hanging off this aluminum. It's probably some kind of aggregate, because aluminum is, the way the trivalent aluminum is a loose acid. It's a sextet. It really doesn't like that, so it will start to aggregate other pieces around here. And it gets too complicated, so I abbreviate it just like that. And at this stage, with dibol, because the double bond is gone, and the reaction of dibol is really a hydroalanation, in analogy to hydroboration to a double bond, since there's no double bond left, it stops. And so it stops here, and then until you throw in water. And when you throw in water on this guy, what happens is the aluminum oxide is hydrolyzed to the hydroxide, as you would expect, and lo and behold, what we have here is a hemiacetal. And hemiacetals fall apart to the corresponding carbonyl compounds. And so that's how you get the aldehyde. Whereas in the case of lithium aluminum hydride, our super aggressive hydride reagent, it just comes in here and kicks out alkoxide to make the corresponding primary alcohol. So it takes the ester down to the primary alcohol, just as it would for a carboxylic acid. Okay, so we can also make ester enolates. After all, it's a carbonyl function. In principle, the position next to the carbonyl is acidic. However, the pKa of an ester is quite a bit higher, about 5 units, than an aldehyde or ketone. And we've settled sort of on 20. It's like for aldehydes, a little lower than 20, but let's call it 20 just to get a ballpark figure. For aldehydes and ketones, these guys are 25. And the reason that they are much less acidic is because this carbonyl function is stabilized relative to aldehydes and ketones by the alkoxy, okay, by resonance. And the corollary of this is that when you make the corresponding enolate, resonance with this oxygen is somewhat compromised by the fact that this oxygen also donates an electron pair by resonance into this function. So overall, that's worth a factor of 100,000, namely 5 pK units. But LDA is definitely a strong enough base. Remember, the pKa of the corresponding amine is about 33, so we're still 8 units higher than this. And so LDA will pull off this guy and make the enolate. And that does behave more or less like a normal carbonyl enolate. You need to preform it, however. You can't make that enolate anymore under equilibrium conditions as we have used them in aldol condensations and Michael additions and Robinson allylations and so on for aldehydes and ketones. There, hydroxide was, well, there the acidity of the aldehyde and ketone was sufficiently high that hydroxide could deprotonate in an equilibrium scenario. You could reach the other side of that equilibrium, even though it's uphill. Here, the extra 5 pK units, so with hydroxide, there would be a pK difference with water in that of 10. That's too high, okay? And so it just doesn't happen. So you can't just take sodium hydroxide and hope to do aldol condensation, stuff like that with esters. It doesn't work. But you can stoichiometrically, in a one-pot procedure, with one equivalent of a very strong base, turn this guy into the corresponding enolate. And at that stage, you can play enolate alkylation chemistry, always bearing in mind the rules for SN2 type reactions. With strong bases, you get elimination. This is even more pronounced for ester enolates because these are even stronger bases than normal aldehyde and ketone enolates, as indicated by that pK difference. Okay? So, but otherwise, if you use substrates that can't do E2, then you're fine. Okay, so for example, this allylic bromide will undergo allylic alkylation, 97%. Can't beat that. Okay? And here are a bunch of other examples. You can do an aldol addition kind of step where you take an aldehyde or ketone, and the enolate will add, like in the first step of the aldol reaction, which is called the aldol addition. You can treat it with oxocyclopropane that will ring open this guy and add a hydroxyethyl group. If you don't work it up with water, because initially you get O- here, but warm it up a little bit, this O- will do an additional elimination to make the corresponding lactone. And methyl, of course, can't eliminate. It's a one-carbon alkylating agent. All right, so this is a good place to have a break. So as was pointed out to me, I added this piece actually originally by trying to rewrite this as another enolate, but it's actually not the same, as you notice. This is an ethoxy, this is methoxy, and this would be derived from acetic acid. This is derived from propanoic acid. So I should add propanoic ester as an additional step with LDA making this guy. So this guy is not that. It's functionally equivalent, but it's not that. So I'll fix that for the future. Whoops. So the last one that we'll discuss are amides. And amides